So the next few sections are all going to be about various integration techniques. So far, really, the only sort of sophisticated technique for integration that we've had is the substitution technique. Like, anytime an integral comes up which we don't immediately know the answer to from a formula, usually that just means that we have to make some sort of integration or substitution, and then things will work out just fine. So we're going to start introducing now a few more techniques to add to our toolbox. And the first one is going to be what's called integration by parts. And you can think of integration by parts as being a sort of product rule for integrals. So, here is a mistake that I see all the time, every semester. Lots of people do it. I honest to God don't know why. There is this assumption that the antiderivative of a product, for example here, this is the antiderivative of x squared times cosine x, people will assume, for really no reason at all, that this is just the product of the antiderivatives. So they'll take the antiderivative of x squared, x cubed over 3, and the antiderivative of cosine, sine, and just leave it there. So I want to emphasize that this is emphatically incorrect. Not only is it incorrect for this particular example, I'm not entirely sure that it's ever correct. I mean, I would have to sit down and work it out, but I have a feeling that this is actually never going to happen. Or if it does happen, then it'll be for a very, very specific and contrived integral. And the reason why integration doesn't work this way is really because differentiation doesn't work that way either. Right? If you differentiate a product of functions, you're not just differentiating the two functions individually and then multiplying them. You have the product rule. Indeed, if we take the right-hand side here and differentiate it, we would have to use the product rule, whereby we would obtain this, and this is not the same as the integrand. So this can't be correct. So what we want to do here is try to figure out some sort of strategy for finding the antiderivative of a product which is correct. And it makes sense that the starting point for such an analysis might be the product rule for derivatives. So, recall what the product rule for derivatives is. Suppose that u and v are functions. I'm going to use the differential notation for derivatives here, because the formulas are going to work out to be nicer that way. So the derivative of the product uv is v times the derivative of u plus u times the derivative of v. Now, let's antidifferentiate both sides of this. So the antiderivative of this, well, that's just going to get rid of the derivative so that we have uv back. And then antidifferentiate these two guys. Well, as the notation suggests, we can cancel out the dx's, quote unquote. Trust me, this works. So that we end up with this formula here. And the way that this is traditionally written is we isolate this bit, the integral u dv, and then take this bit and move it over to the other side. So this is called the integration by parts formula. You can think of it as being maybe the closest thing to a product rule that we have for integrals. It's not immediately obvious how we would use it, though. Like, given an integral, how is this formula, which just seems abstract and like just a collection of symbols, like how does this formula actually help us? Well, we're going to do a bunch of examples that I hope illustrates the use of this formula. But in general, what we want to do is, given an integral like x squared cosine x, we want to take a part of it, say x squared, and identify that with the symbol u. And then take the rest of it, say cosine x dx, and identify that with the dv. Okay? So given an integral, we take part of it, say that that's u, take the other part, say that that's dv. And then once you have made that choice, we fill out the right-hand side, and then we still have an integral that we need to evaluate, but hopefully this integral here on the right-hand side is easier than the one that we started out with, right? So basically what the integration by parts formula is it's giving us a strategy for taking an integral and obtaining from it a different integral, which hopefully is easier. Whether or not it actually happens to be easier depends on how you choose to identify u and dv. So that's basically what I say down here. So yeah, it's best, I think, to do this by way of an example. Okay, so find the antiderivative of x sine x. So this is a product, x times the sine of x. So the first thing that we want to do is we want to let u equal something and dv equal everything else. Well, that immediately raises the question, how should we choose which bit of this is going to be u? Should I let x be u, or should I let sine x be u? So this is one of those things that ultimately you just have to get a lot of experience to be able to tell. But I have found that the following mnemonic works fairly well, at least for the type of problems that you're likely to run into on homeworks and exams and the like. So ILATE. So the way that this works is read down this list, ILATE, and then whichever one of these shows up in the integrand, you let that be u. So read through this in order, and the first one which appears in the integrand, let that be u. So, inverse trigonometric functions. Are there any inverse trig functions here? No. Logarithmic functions. Are there any logarithmic functions here? No. Algebraic functions. So algebraic functions are just like polynomials, things that have square roots in them, rational functions, so like big fractions that have polynomials in them, things like that. Does this have any algebraic functions in it? Yes, it does. X is an algebraic function. I mean, you can think of this as being a polynomial, just with one term in it. So we let u equal x. Now that we have chosen u, we need to choose dv. Now, if we are identifying this integral with this integral here, then once we have chosen u, we have no choice but to let dv be everything else. So if u is equal to x, dv has to be sine x dx, and we are including the differential here. Right, so once you have chosen u, dv has also been determined. So u is x, dv is sine x dx. Now, we want to fill out the right-hand side of this formula here. So what are the ingredients? Well, we need u. Okay, we already have that. We need v. Well, let's see. We don't have v, but we do have dv. So in order to obtain v, we would have to take the antiderivative, right? That's how this notation works. Or at least this notation is very suggestive of that. Yeah, so obtain v, you add up all of the infinitesimal dv's, or in other words, you just take the antiderivative. So that's v. We also need du. So to get du, we need to take the derivative of u. And that's what I'm saying here in this second part. We need to compute du, which is the derivative of u times dx, and v, which is the antiderivative of dv. So du is equal to the derivative of x dx. Well, the derivative of x is just 1, right? So du is equal to dx. Not terribly surprising. As for v, we need to take the antiderivative of all of this stuff. So v is equal to the antiderivative of sine x dx. And this is why it's customary to include the infinitesimal term, since, you know, we're going to end up taking the antiderivative of it. So let's see. The antiderivative of sine is minus cosine. And don't bother about adding the plus c. That's unnecessary when we're doing integration by parts, as it happens. Okay, so now that we have all the ingredients, let us fill in the right-hand side of the integral. So uv minus integral v du. So u is x, v is minus cosine x, minus integral v, so minus cosine x again, du. So du is dx. Okay, so now all we need to do is evaluate this stuff. And this is indeed much more tractable than what we started out with. So let's see, minus a minus becomes plus. And what is the antiderivative of cosine? Well, that is just sine. And there we go. There's our final answer. So not too bad, right? I mean, as long as you get the procedure figured out, then it's basically just rote computation. Granted, it's still easy to make like sign mistakes, as it always is. So you do have to be careful, but not too much creativity going into this. It's basically just you choose u, and then everything else follows from that choice. Okay, let's evaluate the antiderivative of the natural log. Now, this might not immediately seem like the sort of example that we would be interested in, because I introduced this whole idea, this integration by parts thing, as being like a product rule, right? It's for integrating products. And indeed, that is the motivation. But as it happens, this technique is effective for integrating single functions as well. So you can imagine, I mean, you can still imagine that this is a product. It's the product of natural log x and 1. So you can be pedantic like that and say, no, it's still a product. But yeah, this strategy is still useful for integrating single functions. Now in this case, when it comes to figuring out what u is, we really don't have any choice. I mean, we only have a single function in there, so we have to let u be the natural log of x. So if u is the natural log of x, then dv has to be everything else. Well, everything else in this case is just dx. Okay, now we compute du and v. So du is going to be the derivative of natural log x times dx. So that is 1 over x dx. We need to compute v. V is the antiderivative of dv, which in this case is just dx. So what is the antiderivative of 1? Well, that is just x. So again, that shouldn't be terribly surprising. So now that we have all the ingredients, let's fill it out. Let's fill out the formula. So uv minus integral v du. So u is log x. V is x. Minus integral v, so that's x, du. Du ended up being 1 over x dx. Okay, let's simplify this. So I would prefer to write this with the x out front so that there's no confusion about, is this the natural log of x squared? No, it's not. Minus integral. So x over x, those cancel. So we're just anti-differentiating the number 1. So we get x log x minus x. And there we go. That is it. So here we are integrating a product again. Now let's see. We have to choose u. Now this time we have two choices. Either we're going to let it be t squared or we're going to let it be e to the power t. So let's go up to our mnemonic. Inverse trig functions. No. Logarithmic functions. No. Algebraic functions. Yes. T squared is an algebraic function. So let's let that be our u. Then we have no choice but to let dv be everything else. So that's e to the t dt. Now let's fill in the rest of our ingredients. So du is the derivative of t squared dt. The derivative of t squared dt. So that is 2t dt. V is the antiderivative of dv. So that is the antiderivative of e to the t dt. Okay, well, that's just e to the t again. Remember, the exponential function base e had that property that it is unchanged under differentiation, and consequently, it's unchanged under anti-differentiation as well. So, now all we need to do is fill out the ingredients. So, u is t squared. V is e to the t minus integral v, so that's e to the t, du. du is 2t dt. Okay, so let's clean this up a little bit. That 2 I can just pull out. Okay. Now, we still have to evaluate this integral t e to the t, which it's not immediately obvious how we would do that. But you might notice we are once again in a situation where we're taking the antiderivative of a product. So, let's just use the integration by parts formula again. Right? I mean, there's no rule that says we only have to use it once. We use it as many times as we need. Right? So let's see. Once again, let's start from the top. We need to choose a u. So Inverse trig functions, no. Logarithmic functions, no. Algebraic functions, yes. T is an algebraic function. So then dv is equal to e to the t dt. So we just go through the same procedure again. So du is equal to the derivative of t dt. So that is 1 dt. V is equal to the antiderivative of e to the t dt. So that is just e to the t again. And now let's use the integration by parts formula. Now notice that for this bit, I am only focusing on this integral over here. So this is not going to be our final answer. This is just going to be an intermediate step. So once we have obtained this integral, of course, I'm then going to have to take it and plug it back in to get our final answer. So don't lose track of, you know, the question that we're actually addressing here. So let's see. U is t, v is e to the t, minus integral v, that's e to the t, du, that's dt in this case. Okay, and now we are in the position where we can actually evaluate this because, you know, antiderivative of e to the t is just e to the t again. And I'm not putting a plus c because we don't need to do that until the very end. And like I said, this is just an intermediate step. So yeah, to get our final answer, plug this into the original integral. So the original integral was this. And that was equal to all of this. But then, instead of this integral here, we have this. And now we can add the plus c. Although, we should still clean this up a little bit, just because. So if I distribute that 2 through, we get minus 2 t e to the t plus 2 e to the t plus c. And then we can leave it at that. No, you know what? I want to factor that e to the t out. That's bothering me. So t squared minus 2t plus 2. There. That looks much better. I mean, it doesn't really matter, but mathematics has an aesthetic component to it. All right. So far, I mean, I think these examples are pretty straightforward. Now, granted, they could be made a lot more difficult just by increasing the complexity of the derivatives and antiderivatives involved. You know, maybe you'll get an example where you have to use integration by parts 3 times, 4 times even. I mean, I don't think we'll see anything like that, but 3 times isn't unheard of. So really, it's just a question of being organized and keeping all of your computations organized. And don't lose track of the original question that's being asked. But each individual step should be pretty straightforward, I think. Now, this example that we're going to do here is sort of a strange one. So, but I think it's really cool. So bear with me. So e to the x sine x. So once again, we are integrating a product. So that suggests that integration by parts is going to be useful. Now, let's go, we have to choose u. So let's go through the mnemonic. I, inverse trig functions, no. L, logarithmic functions, no. A, algebraic functions. No. T, trigonometric functions. Yes. So we have a sine x. So let's let u equal sine x. Then we have no choice but to let dv be e to the x dx. So, everything else. Now let's fill out the checklist. So du is the derivative of sine dx. So the derivative of sine is cosine. As for v is the antiderivative of dv. So that's e to the x. And once again, that is unchanged. Okay, so now let's fill in the data. So this is equal to uv minus integral v du. So u is sine x. V is e to the x minus integral v is e to the x again. Du is cosine x dx. Okay, so it appears like we need to do integration by parts again, because the integral that we ended up with is no easier than the integral that we started with. Basically, all we've done is we've just changed sine for cosine. So let's do it again. On this dude. So once again, if we go through I late, none of the functions are involved until we get to trigonometric functions, in which case we have a cosine. So let u equal cosine x. Then we have no choice but to let dv be e to the x dx. And now let's fill in the ingredients. So du, that is the derivative of cosine dx. So the derivative of cosine is minus sine. V is the antiderivative of dv, so that's the antiderivative of e to the x. So that is just e to the x again. And then we plug in our data. Again, be careful, because this is not going to be our final answer. I am only looking at this latter integral here. So we still have to plug this in to our original expression after we're done with this iteration. So u is cosine x. V is e to the x minus integral v is e to the x, du is minus sine x dx. And I don't like this negative and negative hanging out right next to each other, so I'm just going to pull that out front. Like so. Huh. Well, this isn't great. What's the integral that we're trying to figure out? It's e to the x sine x. What's the integral that we've ended up with? It's e to the x sine x. So integration by parts has taken us for a loop. We've gone in a circle. We've gone nowhere. Or have we? So here's something pretty clever. I'm not saying that because, like, I didn't come up with this. This is an example that's probably hundreds of years old by now. But I remember thinking when I first saw this as an undergraduate, I was like, wow, that's really cool. So let's just go ahead and take this and substitute it into our original integral anyway. So it appears as if we have gotten nowhere. Regardless, let's substitute this into our original integral. So the original integral was all of this. And then, instead of this latter chunk, we got all of this. Oh, hang on, I need to be careful. I need to put parentheses around that. There we go. And then let's clean this up a little bit. So I don't like having this e to the x out front. I much prefer it like that. Then if I distribute this minus through, so minus e to the x cosine x minus integral e to the x sine x. I don't need this space there. There we go. So it does appear as if we've gotten nowhere. But wait a second. Why don't I just take this e to the x sine x and add it to the other side? Why not, right? I mean, they're exactly the same, so let's just combine like terms. And this is the bit that I thought was super clever when I saw it, because like there's no reason why you shouldn't be able to add two integrals together as if they were like terms. They clearly are. It's just, you know, you wouldn't immediately think to do that, I don't think. At least I certainly wouldn't have. So take this dude, add it to the other side, and we get 2 integral e to the x sine x equals e to the x sine x minus e to the x sine x. So let's factor that e to the x out. Like so. So hey, now just divide both sides by 2, and miraculously, we are finished. So it turns out we weren't going in circles at all. Yep. So that's pretty neat. And then we can refrain from adding the plus c until the very, very end. You know what? Let me save factoring out the e to the x for the last step. Just make it a little bit more clear what we're doing here. Because I've literally just taken this chunk and moved it to the other side. And then everything else remains the same. And then after that, I can factor out the e to the x and then divide both sides by 2. But yeah, that's really neat. That's I would say maybe an unexpected strategy to arise from using integration by parts. And every time you see an exponential function and a trig function right next to each other, you're going to have to use some sort of strategy like this. Because the thing with the thing with trig functions really is that if you continually differentiate or anti-differentiate them, you're just going to end up going in a circle. At least for the sine and cosines. For tangents and secants, they sort of explode out of control. But with sines and cosines, at least, continued differentiation or continued anti-differentiation just leads you in a loop, right? It goes sine, cosine, minus cosine, sine, cosine, minus cosine, whatever. Similarly with e to the x, continued differentiation and anti-differentiation is going to do nothing. So integration by parts, sort of by necessity, is going to get led into a circle with these sorts of functions. But, as we can see, that's not necessarily a bad thing. So, as one final example, let's do a definite integral. And when you're using integration by parts to evaluate definite integrals,